let me go turn the lights out. And this is, I think, really a super video. It really, I found out more about the Earth than I think I've ever learned before. And you can go watch this anytime because I sent this to you. If you want to, have me send it again, let me know. So here we are. This is just the preview of it now. So it'll give you an overview of what we're going to see.
Our planet, Earth. You may think you know it well, but a startling new picture is emerging of a world shaped by forces more dynamic and intertwined than we ever imagined, raising possibilities that defy common sense. How can sandstorms in the Sahara Desert transform the Amazon rainforest over 5,000 miles away? In the frigid ocean beneath Antarctica, how can a vast undersea waterfall 500 times bigger than Niagara Falls lead to a gigantic feeding frenzy near the equator? And how can warm water streaming past the coast of Africa trigger a weather catastrophe half a world away in the southern United States? Scientists have begun to find surprising answers to these and other profound questions, thanks to a network of satellites orbiting high above the Earth. Ever watchful, their senses extend far beyond what our eyes can see.
It's really the last bastion of human discovery. We're discovering new things every day.
What are these hidden forces that rule our world? How are the oceans, the continents, the atmosphere, and even the sun bound together? And how do they affect all living things? For the first time, we can understand how earth, fire, wind, and water join together to create the dynamic environments that shape life in all its forms.
Their interaction is what has created the environment, the diversity, the kind of life we see on Earth today.
With astonishing images created from a wealth of new information from satellites, this is our planet as never seen before. Earth from space, right now on Nova.
Major funding for NOVA is provided by the following: the David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. And by the Corporation for Public Broadcasting. And by contributions to your PBS station from viewers like you. Thank you. And Millicent Bell, through the Millicent and Eugene Bell Foundation. Major funding for Earth from Space is provided by the Candida Fund, furthering the values that contribute to a healthy planet.
Since humans first ventured into space, some of the greatest gifts of exploration have been the new views of our home. Who can forget the iconic Earthrise images of the Apollo era? And now from the International Space Station, we have these spectacular vistas. The blue marble is finally revealing its secrets. It's a planet alive with activity and constant change. its surface transformed by humans, yet still ruled by powerful natural forces that we are only beginning to understand.
It's just spectacular when you view it from space. It's teeming with diversity, with beauty. Amazing colors, you know, the blues and the greens and the whites.
You see the world as one huge system, all linked through the atmosphere and the oceans, rolling its way around the sun.
So what is it that shapes Earth's dynamic face? What are the essential ingredients, and how do they combine to generate and sustain all life? How do the natural forces that surround us work together to create an engine powerful enough to nourish and drive life forward in all its diversity? Our best hope for answers may come from above. Orbiting over our heads are 120 satellites, keeping watch from space. Most operate at altitudes ranging from a few hundred miles above the surface of the planet to as high as 25,000 miles. Each one of these Earth-observing satellites reveals a different piece of the puzzle. Each carries an array of exquisitely sensitive detectors designed to reveal what would otherwise be hidden from our view.
The satellites are absolutely amazing because not only can we see the visible things from space, but also we can see things that aren't visible to the human eye. So satellites are enabling us to turn what are invisible processes into visible things we can see and then understand.
To see how our world works, in this program we have taken information provided by satellites, combined it with computer models, and rendered the results in these scientifically accurate graphics. With the invisible now revealed, we can see Earth as an endlessly changing system. These images will show in great detail how sunlight, moisture, land, and atmosphere interact in unexpected ways, with seemingly local events often triggered by forces far away in space and time. And with these new insights, for the first time, scientists can begin to understand the intimate relationship between the planet and all the living things it supports.
It's really the thrill, because it matters so much, of piecing together the story of what the Earth is doing, how it's changing, why it's changing, and how ultimately that affects humans.
The first piece of the puzzle is in understanding the massive influence the sun, from 93 million miles away, has on our planet.
The world's continuously bathed in a flow of energy from the sun. And that warms the Earth. Everything that you can see that lives and breathes and moves on the Earth is pushed by the sun.
Now, an electronic eye in space can measure the impact of the sun's energy all around the Earth. One of NASA's newest satellites, named for a meteorologist, Polar Orbiting Suomi, launched in 2011, provides the view. The spacecraft is the size of a small school bus. It orbits 500 miles up, circling the planet 14 times a day. On board, it carries 5 separate sensors that enable it to see things invisible to human eyes. The light that we can see is confined to a narrow band of electromagnetic radiation, just a tiny portion of what the satellite can pick up. Electromagnetic radiation spans a spectrum that goes far beyond the familiar colors of the rainbow.
If you were to consider the full spectrum to be a line that stretched from New York City to Los Angeles, the piece that our eyes could see would be about the size of a dime. There is so much other information out there available to us, and that's in large part what these satellites do.
One of this satellite's key instruments is called CERES, an acronym for Clouds and Earth's Radiant Energy System. It detects a broad range of the spectrum, including the very short and very long wavelengths of light in the ultraviolet and infrared that we can't see. This is a Ceres eye view of the planet. Anything that emits heat gives off infrared radiation, so the Ceres data shows the Earth in shades of heat, accurate to a fraction of a degree. It reveals how the planet as a whole reacts to sunlight, both absorbing and reflecting the radiation coming from our local star. At the poles, the sun strikes at an oblique angle, and what little light there is gets reflected back out to space by the ice and clouds. These are the primary reasons why the poles remain cool. At the equator, it's a very different story. Not only does the planet receive more direct sunlight here, the lack of ice means that less of the sun's energy is reflected back into space. And at the equator, the sun's concentrated energy fuels a heat engine that can trigger weather events around the world. Perhaps the best place to see the impact of the sun's heat is an area in the Atlantic just north of the equator and west of Africa, the coastal waters of the Cape Verde Islands. Here, the sea provides a living. The local fishermen keep a careful eye on the weather. They know that storms can bring a good catch. Turbulent weather stirs up nutrients from the deep, attracting great shoals of fish. It's the hottest time of the year, and the sun beats down relentlessly. By late afternoon, the huge inflow of heat energy has led to the buildup of large cloud formations. Sometimes these formations develop into massive storms. It's a process that satellites are revealing in fine detail. Circling above the fishermen is a NASA satellite called Aqua, Latin for water. It orbits the poles. One of its key tasks is to monitor the complex interaction between sunlight and water.
Aqua satellite is one of NASA's flagship satellites. Its primary function is to study the hydrologic cycle on Earth. Vapor in the atmosphere, liquid ocean, the temperature of that ocean, and the ice.
One of Aqua's instruments looks down at the sea around Cape Verde, again in infrared, sensing heat. Highlighted here in yellow, over 1 million square miles of ocean reaches a critical temperature, 80 degrees. At this temperature, the sea is evaporating fast, producing an invisible gas, water vapor.
By looking at the infrared, the Aqua satellite is able to measure the amount of water vapor evaporating from the surface of the ocean.
Aqua shows that this area is producing millions of tons of water vapor every hour. Based on that data, it's possible to create an image of what the vapor might look like if these fishermen could actually see it in the air around them. Water vapor is much lighter than air, and vast columns rise upward directly from the surface of the sea. The water vapor carries with it heat, the energy of the sun.
Well, water vapor is like invisible energy. It's like molecules escaping the ocean, taking heat energy with them, and they're like little mobile solar collectors that are zipping around the atmosphere.
Half a mile up, as the air cools, the water vapor condenses back into liquid water, tiny droplets that form vast clouds. The vapor releases the sun's energy, the heat it received earlier. The result is a storm.
Molecules condense in the atmosphere and become liquid again, and when that happens, that heat is given off into the atmosphere, and it warms the atmosphere, and that's the heat that powers storm systems.
In the worst storms, the heat captured by the water vapor is equivalent to up to 200 times the global production of electricity at any given moment. The process of evaporation results in something we don't need special instruments to see. The rising heat drives the clouds up to 10 miles high. As the clouds rise upward, the Earth's rotation causes them to spin. The thunderclouds merge into a vast vortex. This is the birth of a hurricane. It is 2005, the busiest hurricane season on record. On August 27th, a meteorological satellite is tracking a Category 3 hurricane that started in the Bahamas. Its name is Hurricane Katrina. Throughout the region, there is one question on everyone's mind. Will the hurricane hit land, or will it blow itself out? The answer may come from a NASA satellite called TRMM, the Tropical Rainfall Measuring Mission. TRMM is equipped with a radar and imager that operate in the microwave range of the spectrum. These are higher in energy and shorter in wavelength than other radio waves. The instruments bounce microwaves off raindrops in the clouds, allowing scientists to build a three-dimensional model of the internal structure of a hurricane.
We can actually look at microwave energy, which is generated within the clouds and coming from the ocean surface. It's almost as if the clouds are now invisible to us. We can see right through them, like taking a CAT scan to look inside those clouds.
This satellite is a powerful tool. And now, its sensors reveal something ominous. Huge vertical columns of warm water vapor burst up from near the center of the storm. Almost like hurricanes within hurricanes, these climbing vortices deliver added infusions of energy into the heart of the storm, fueling its growth even more. These new sources of energy are called hot towers.
If they occur in the right place at the right time near the very center of the system, they could be like a giant spark plug that gets that whole engine running at very, very high speed.
The hot towers draw more and more water vapor off the ocean. This triggers a feedback loop that leads to a runaway reaction. In just 24 hours, Hurricane Katrina grows into a Category 5 monster. All this violence is a direct result of the power of the sun on the ocean. Ferocious winds blow for 2 days straight, reaching 175 miles an hour. 12 twisting steel like paper and ripping apart homes and buildings. Over 3 trillion gallons of rain a day, and a massive tidal surge from the Gulf of Mexico combine to inundate whole areas of the Gulf Coast. Katrina leaves its mark across 90,000 square miles. Over 1 million people are displaced. Katrina becomes the standard by which future hurricanes will be assessed. But even this extreme hurricane is just a tiny brushstroke in a much bigger picture. A picture of how the sun drives water around the entire planet, with radically different effects in different places, all under the watchful gaze of our eyes in space. Take just a single day in July. In New York, commuters swelter in 95-degree heat. Searing winds pump hot air into the region from the south, creating oppressive, humid conditions. 7,000 miles away, in Mumbai, India, commuters here struggle to cope with torrential rain. The deluge comes so fast that the streets are flooded in hours. Meanwhile, in Chile, the desert of the Atacama is almost totally dry. There are places here where rainfall has never been recorded. Such diverse environments thousands of miles apart appear totally unrelated. But by pulling back for a wider view, we can see that they are in fact intimately connected. Orbiting 22,000 miles from Earth's surface is a chain of 5 weather-tracking spacecraft, including this one, NASA's GOES East. GOES is an acronym for Geostationary Operational Environmental Satellite. Each moves in a fixed position relative to the Earth, called a geostationary orbit. They always look down on the same parts of the planet. The combined data from these 5 satellites gives scientists a unique perspective on the Earth.
By having several of them located at different positions around the equator, we're able to get a view of the whole Earth 24 hours a day.
By observing the entire Earth, these satellites reveal how energy moves throughout the globe, beginning with the impact of the sun on water. The process is the same everywhere, but the outcome will be very different in different places. Converted from the numerical data, these 5 circles graphically depict what the satellites actually sense. They reveal the total picture of water vapor produced on Earth in a single frame. Seen here in fast forward, 1 second is equal to a day. It shows how water vapor produced at the equator continuously transports the sun's energy towards the poles. Local landscapes and topography affect the vapor's impact, with results unique to each region. In India, at the end of July, the warm water vapor is drawn from over the ocean by the difference in temperature between land and sea. Rising to high altitude, the vapor cools over the land and condenses back into water. We call the result the Asian monsoon. Nearly 1 trillion tons of rain falls out of the sky, transforming parched land into fertile plains. The monsoon eventually moves to the east, reaching China, where it floods the paddies that are ideal for growing rice. This process helps provide food for 3 billion people, almost half the world's population. Meanwhile, on the other side of the world in South America, westbound winds drive water vapor across the high peaks of the Andes. The altitude strips the air of its moisture, which falls as snow on the mountains, creating, on the far side in central Chile, the arid desert of the Atacama. That same July day, in the eastern United States, hot, moist air surges north, straight from the Gulf of Mexico. With no natural barrier in the way, more than 100 million Americans, from Memphis to New York, swelter in the summer heat. This graphic, based on information provided by satellites, depicts the interaction between the atmosphere and the oceans as they connect in a global pattern of circulation that results in our local weather.
The satellite data shows that it's all one interconnected system, but that in different parts of the world, different processes are happening. We can see the monsoons and their effect. We can see the effect on deserts in a different part of the world. And that together shows us how the water vapor is connecting with life on Earth.
But this vast cycle of sunlight, water, and land is just one pattern among many on this planet we call home. A cycle with even greater consequences for the long-term climate involves extreme cold. To see how that works, we have to turn the Earth upside down and look at it from below. Antarctica remains the Earth's last great wilderness, a vast frozen continent plunged in darkness for almost 6 months of each year. In winter, temperatures can drop below -110 degrees Fahrenheit, and an incessant 100-mile-an-hour gale blows. It's hard to believe that anything life-giving could start here, in this bleak place. But that's exactly what happens. Antarctica's ice plays a vital part in maintaining global climate, sustaining life even in lush, warm jungles thousands of miles away.
Antarctica as a fundamental element of the climate system. And while it may sit silently and majestically at the edge of the planet for very few to see, things go on there that spread out all over the world, that affect the world as a whole.
It's a paradox that such a bleak and barren place is so critical to life on our planet. On average, it's 43 degrees colder than the North Pole. Why should Antarctica be so much colder? And how does that affect the rest of the world? The detectors on NASA's polar orbiting satellite Suomi provide part of the answer. The instruments sense in the infrared and ultraviolet parts of the spectrum. They show that the poles receive little of the sun's energy and reflect most of it back out into space. That's one reason why the poles stay cold. But there's another factor that makes Antarctica colder still. This image has been pieced together from 17 different satellites that sense the infrared, or heat. The continental mass of Antarctica lies beneath this swirling maelstrom of cloud. A computer model of the data shows what happens as the warm, moist air arriving from the tropics collides with the cold air over the South Pole. The result is a massive storm system. And just like a hurricane, it rotates as a result of the spin of the Earth. Only this is much larger than a hurricane, 4,000 miles in diameter.
Where that cold air and warm air meet high up in the atmosphere, the air starts to rotate around Antarctica. The winds can be up in the atmosphere as much as 200 miles an hour.
This circulation pattern is called the polar jet, a ceaseless circle of wind and storms. The relentless clockwise wind, seen here in yellow, drives the seawater below, shown in light blue.
Those strong winds are sending a jet around in the ocean, and it's driving an ocean circulation that is felt almost all the way to the bottom of the ocean, 2.5 miles deep.
The Southern Ocean rings the continent, with no land to interrupt a vast body of moving water. This is the Antarctic Circumpolar Current. And these are the screaming 60s, the roughest, most dangerous seas on the planet. Here, storms rage almost every day of the year, whipping hundreds of trillions of gallons of water into a ceaseless frenzy. Now, the infrared instrument on the Aqua satellite, which senses atmospheric temperature, puts the pieces of this puzzle together. The winds of the polar jet and the water of the circumpolar current together form an impenetrable barrier around Antarctica, isolating it from the rest of the planet and depriving it of warmth. That is why the whole region remains exceptionally cold all year round.
What's incredible about what the satellites tell us is that the movement of air, and actually the movement of ocean current, around the perimeter of Antarctica isolates the continent from the rest of the world.
So why is this relentless cold so important to the planet, way beyond Antarctica? The answer lies in a remarkable property of water: what happens when it freezes.
I just wanted to stop it and give you a chance to stand up and stretch a little bit. I know it's kind of hard to sit there. Anybody have any comments or questions about that? Do you remember all of those? Yeah, question.
How long is that satellite supposed to function? Like its lifespan?
Which one?
The Oswald.
I don't know. Probably normally you design those kind of satellites for, like, 7 or 8 years. Some of them, like the big geostationary communication satellites, they had 7, 8 years on them. Some of them went as long as 15 years. So it depends on the satellite, and these satellites have to fly in a particular orbit, and they have to have some thrusters on them to keep them in that orbit. And especially, you remember the ones that they showed, the 5 of them there that were out, geostationary satellites? They have to remain within a geographic box out there in order to be able to orbit the Earth like they do. So one of the functions of how long a satellite will last is how long is the fuel that they've got to stay in that. The other thing is, how long do the batteries last? Those are the things that are most apt to determine the life of a satellite. So one of the things, kind of pay attention, and I didn't tell you at the beginning, but write down the names of the satellites, and maybe we'll take and look up some of these. They talked about the NOAA satellites, right? Those are weather satellites. They have polar orbiting, and then they have the geostationary satellites that are looking at the weather all the time. And I thought and I'd never known as much about how the hurricanes form off of the coast, the west coast of Africa, and how it picks up the energy there and comes across. I thought it was really, really quite interesting. And then to see what happened with Katrina, why it was so devastating is the conditions were just right for it to have a lot of energy that had picked up the water in the Gulf and then brought out all of it in. And the one thing to think about in the hurricanes, what is the storm surge? What is that? Anybody know? When these hurricanes are coming across the water, they're actually pushing the water. So not only do you get the rain that's coming down, this actually raises the sea level in front of the hurricane, and when it come into New Orleans, it just pushed all that water. And what's the elevation of New Orleans? Anybody know? Yeah, it's below sea level. That's a catastrophe, right? So this storm surge can be as bad as the rain itself. Not only are you getting water coming in from the ocean, and that's what happened up in New Jersey, is this storm surge come in, and what happened? All this rain happened, so you got water coming from both directions. But watch this. This is one of the things I never knew here. To me, this is a fascinating thing about Antarctica. Antarctica, to me, is a fascinating place anyway to see what goes on. But watch here, they're talking about, and you'll see, did you see the ice pack grow and then shrink? So during the winter, the ice pack grows over the Antarctic, and what actually happens is the ice that forms at the North Pole, actually it kind of starts to slide down because it's under a bunch of mountains, and it slides down, as well as the ice that forms in the winter there, and then these big icebergs break off. But watch for a thing here that I never knew. What happens to the iceberg? And because they're formed and they've got salt in them, what happens to the salt? Watch that. Is this interesting? Yeah. I thought it's a fascinating film. I hope you do too, because this is what space is all about. Space is about those instruments that they've got on there. The space is about making those spacecraft. I hope that someday you get a chance to work on satellites like that or analyze the data. I think it's cool. Can you imagine how little we knew before we had these satellites that could do that? What would it have been like in Katrina if we had not had weather satellites to predict it? It would have been worse, right? Did it help them when the hurricane that hit New York? Did they prepare for it? Probably not enough, but they prepared for it, right? So there's some really interesting things that that go on. And what did they say? How many satellites were up there that was affecting? How much? 120 satellites. Yeah, yeah. I thought it was pretty good. Okay, well let's go ahead and stretch it a little bit. Next time we watch one of these, bring some drinks and popcorn. Let's live it up a little bit. I get to eat your popcorn. I like popcorn. All right. Here we go.
The Aqua satellite reveals the start of the process. It sweeps the surface with its microwave scanner, looking through the clouds to detect the distinct signature of ice.
The microwave instruments on the satellite enable us to see through the clouds to the sea ice around Antarctica throughout the year. What's particularly incredible about that is we're able to take measurements of the sea ice in places where, as scientists, as humans, we can't even go.
This satellite gives us an accurate picture of the extent of sea ice around Antarctica over the course of a year. Seen here in summer, Antarctica is nearly 1.5 times the size of the United States, covered in ice. But in winter, it grows even more. Over 5.5 million square miles of ice form around the continent. It grows to the size of all of Africa. This vast ice formation has a profound effect on life across the planet. How can its impact extend so far? One of the best places to understand the power of ice is the huge bay along the northwestern coast of Antarctica, the Weddell Sea. Here, a constant gale blows and cools the seawater to freezing temperatures. Once the upper layer of ocean falls below 29 degrees Fahrenheit, a critical threshold is crossed. The surface of the ocean begins to freeze. At a microscopic level, tiny crystals start to grow, knitting themselves together. As the crystals bond, they expel salt into the water. The salt forms brine that drips down long, narrow tubes and holes in the ice as it forms. The brine is denser than regular seawater, and it sinks downwards. As winter's grip tightens, the formation of ice speeds up and spreads. Soon, large slicks appear on the surface and thicken into a solid mass. What started as a microscopic process can soon be seen from space. Each year, more than 200 billion tons of ice form in the Weddell Sea alone, releasing tens of trillions of tons of dense brine into the ocean. The fate of all this brine is a mystery. The crucial question is, where does it all go? A satellite called Jason, jointly operated by NASA and the French Space Agency, is providing new answers. Jason bounces radar signals off the surface of the ocean to measure its height. The instrument also reveals the shape of the sea floor far below.
We can make very accurate maps of submarine bathymetry, but we don't do that directly. We do that by measuring the surface of the sea from space very, very accurately and over time.
Jason's radar is so precise that it can detect minute changes in the level of the sea surface produced by the peaks and valleys of the terrain below. The data makes it possible to map the ocean floor.
You have a satellite that's up there 500 miles up in space, and it's returning an accuracy of a little less than ½ an inch. What that means is, I stuck this instrument in Washington, D.C., say, and I'm looking at a crowd of people in Boston, and I can tell you whether or not their toes are over the curb or not. That's what the satellite is doing.
The satellite data allows scientists to make a three-dimensional map of the ocean floor beneath the Weddell Sea. It reveals a vast chasm 2 miles deep off Antarctica's continental shelf. As the brine descends into the ocean, it eventually falls over this precipice. Other sensors attached to the sea floor track the flow of the brine as it sinks.
What we're really excited about is that we're able to take that data that shows us what the bottom of the ocean looks like and combine it with data from sensors under the water. And that enables us to look at the dense water and where it goes.
Combining data from satellites and undersea instruments, scientists can reconstruct what is happening hidden beneath the ice. What they learn is astounding. $1 trillion gallons of salty brine plunge down through the Weddell Sea every hour, a torrent equivalent to the volume of 500 Niagara Falls. The brine spreads out towards the edge of the Antarctic continental shelf and then falls into the chasm revealed by Jason. A vast submarine waterfall plummets downward. The cold, dense brine falls slowly, silently, into the abyss, 2 miles down to the ocean floor below. It will not resurface for hundreds of years. What happens to the brine next is still being investigated, but computer models combined with satellite data are helping scientists to figure out where it goes. This animation shows the undersea current in action. The purple area is the brine. The outflow from Antarctica drives the salty water towards the equator, along the sea floor.
All the water in the bottom of every ocean around the globe has its start within 6 miles of the Antarctic continent. It creates the coldest, densest water that's on the planet.
The cold, salty liquid becomes part of a worldwide circulation system, stirring and cooling all the world's oceans. Leaving Antarctica, it has embarked on a journey that could take 1,000 years to complete. As it migrates towards the equator, the cold bottom current mixes with fresher and warmer water and slowly rises. It then joins other ocean currents and eventually returns south, where it cools once more. Finally returning to Antarctica, the seawater freezes and releases its salt again, completing the cycle.